Okay, we're back for our last little bit of discussion on electric potential for the day. So, again, electric potential, kind of a little bit of a confusing concept. What it really boils down to is it allows us to determine how much energy, how much the energy is changing per unit of charge when we take a charge and move it from one place to another in an electric field, okay? And again, the reason the energy is changing is because you have charges changing their distance away from one another. Electrostatic forces are doing work, therefore the energy is changing. Another way you can think about it, I was thinking about this a minute ago, is you can think of electric potential difference or voltage. You can kind of think of it as almost like a little idea of like how much energy each little charge is carrying. Okay, that's a little bit of a simplification, but it might help some people. Anyways, when we're talking about charges, a lot of times we're talking about very, very small charges. So if you look at number 3, it says if one electron is moved through a potential difference of 1 volt, how much work is done? Well, this should be pretty easy to figure out because we know that the equation that we need is V equals W over Q. We're looking for how much work is done, so that's W. So we know W equals Q times V. And let's see here, 1 electron, well, how much charge does that have in coulombs? We know an electron is an elementary charge, and an elementary charge has a charge of 1.6 times 10 to the negative 19th coulombs. So that's my charge, that's fine. And it's moved through a potential difference of 1 volt. In other words, the difference in voltage between 2 spots in this electric field is 1 volt. Well, how much work is done? Well, this is pretty easy. 1.6 times 10 to the negative 19th joules of work is done. That's really, really small, right? And that's going to be fairly common, a very small amount of work being done if we're dealing with very small charges, like we very well are a lot of times. This is tiny. Because this is so small, we created an energy unit known as the electron volt. To make it easier to measure how much energy small particles receive from moving through a certain potential difference. So the definition of, and it's literally just called an electron volt. You're just taking those 2 words, electron and volt, and slamming them together. The symbol for electron volt is EV. You'll even notice the symbol or the unit itself is kind of like taking 2 things and just pushing them together. E standing for electron or elementary charge, and V standing for volt. This is the energy gained by 1 elementary charge, which could be an electron, could also be a proton, moving through a potential difference of 1 volt. On the reference tables, there's a conversion, and you might have noticed before that there is this thing on in the conversions or the constants section says 1 electron volt, EV. It says 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. There we go. 1 EV equals 1.6 times 10 to the negative 19th joules. So it's very, very small. But it's useful for talking about very small types of energy, so we don't have to just keep using the scientific notation over and over again. So let's look at number 4. If 3 protons are moved through a potential difference of 7 volts, how much energy is gained? Let's do it the old way first, okay? Initially, what we would have done is we would have done, okay, V equals W over Q. We would have said the voltage difference is 7 volts. We would have tried to find the work done. Let's see, 3 protons. Well, each proton has the same charge as an elementary charge, 1.6 times 10 to the negative 19th coulombs. If there's 3 of them, then that means we do 3 times 1.6, e negative 19th, and that's 4.8 times 10 to the negative 19th coulombs. We solve this for W. We end up just multiplying this over to the other side to solve for W, and we get 3.36 times 10 to the negative 18th joules. Now that's the old way. Let's do this the new way, okay? Let's see a new way to do this. If we have 3 protons, we're still going to use the same equation, but if we have 3 protons and we're using, let's say we want, that's a really small number, we want our answer maybe in electron volts. Let's try this. 7 volts equals W, and then how many elementary charges do we have? Well, we have 3, 3e. This is going to become W equals 3e times 7 volts, 3 elementary charges times 7 volts, and isn't that equal to 21, and then the units are eV, in other words, electron volts? We see that the work done is 21 eV. And just to make sure that you understand that this is the same thing, if I take 21 eV and I convert it to joules, in other words, if I take 21 and I multiply by 1.6 times 10 to the negative 19th, I get the exact same thing. So in certain cases, when we're dealing with electric potential, you can't really do this for electric fields, you can't do this for electric forces. But when we're dealing with electric potential differences, sometimes the answer might be in electron volts, or something, the work done, the energy might be asked for in electron volts. And it makes the calculations actually quite a bit easier. Because if you're just counting up the number of elementary charges, well, that's very easy to do. If you have 3 protons, it's 3 elementary charges. You have 4 electrons, it's 4 elementary charges. Finding the work done or the energy gained or lost or transferred in elementary charges is really actually, or in electron volts, is really actually pretty simple. You can't do it all the time, but it is something that will get asked every once in a while. Okay, so we should know, and we'll come back to electron volts later on, you should know how to work with electron volts. Okay, it's just another unit of measurement for energy. Our last question here kind of will lead into our circuit discussion. A battery has a potential difference of 6 volts between its terminals. Okay, so that means that if something goes from one terminal of the battery to the other, that means it must have transferred 6 joules of energy for every coulomb of charge that flows through. Okay, that's what that means. If a certain charge moves from the positive terminal to the negative terminal and loses 0.03 joules of electric potential energy along the way, what was the magnitude of that charge? We're going to go back to our equation. I know that the voltage difference is 6 volts, tells us how much energy is lost per charge. We know that this particular charge lost 0.03 joules. We want to know how big that charge was. Based on how much it lost and the voltage difference it went through, how much charge did that charge have? We solve for Q. We see that if we cross multiply, we get, here I'll just show you, 6Q equals 0.03. We end up having to divide by 6 both places. So we end up with 0.03 divided by 6. Q is 0.005 coulombs, or 5 times 10 to the negative third. 1, 2, 3. Yep, coulombs. Okay, that concludes our electric potential notes. This is now you can see it. This is another challenging concept. It really took me a while, probably until I was, honestly, probably until I was in the upper levels of college, or even when I was teaching it for the first time, that I felt like I really understood what electric potential meant. Okay? It's the change in energy divided by how much charge is moving from place to place in an electric field. Okay? It's a very tricky concept. You're going to have to think about that quite a lot in order to have it make sense. Okay? There's some things that you really do have to focus on in order to have them, in order to, comprehend them and make sense of them. I think this is one of them. So, if you have any questions, please don't hesitate to ask. Your homework is going to be to complete the electric potential homework, which is typically, it's really not too bad. It's one of the easier homeworks, I think. If you have any questions, please let me know. Please reach out. Let me know if anything is going wrong, if you need absolutely anything. I hope you're all staying safe and healthy, and I look forward to seeing you hopefully in the not too distant future. All right? Have a nice day. Bye.